Okay, in this video, we will learn to do the inference for multiple regression using ANOVA. So we have seen the ANOVA in the simple linear regression, but today we will learn more details about the ANOVA method. So basically, it's not just an alternative for testing the slopes. It is actually a method for comparing a full model and a reduced model. And we will see. So what is ANOVA? It is analysis of variance, and this method is to use the sum of squares to construct a test statistic for comparing nested models. So what are the nested models? A nested models is a pair of models such that one contains all the parameters of the other. Here are two examples. For the full model is a multiple regression, and the predictors are x and x squared. We have three parameters: beta naught, beta 1, beta 2. And the reduced model is y equals beta naught plus beta 1 xi plus epsilon I. And this is called a reduced model because this model has one less predictor than the full model. But it is nested in the full model because we can see that the predictor used here is also in the full model. So it's just using one less predictor than the full model, which is the x squared. And there is one less parameter than the full model. Okay, and the next one. So this is also a multiple regression model. We have two predictors, x1 and x2. And there are three parameters, beta naught, beta 1, and beta 2. And in the reduced model, so this is a very common reduced model where you don't have any predictors. So it is nested in any multiple regressions. There is only an intercept and so one parameter for this model. And it is two parameters less than the full model. And here are the SST, SSR, and SSE. Yeah, we have seen this a lot of times. And this total sum of squares, SST, is the total amount of variation in the response. Okay. So it is using the square distance from the center to measure the variation. And regression sum of squares is the amount of variation in the response explained by the model. Okay. So we have the fitted response y hat by plugging the xi's to the fitted regression line and or the regression surface, and the y bar is also the center. So this is the variation explained by the model. And the last one is the error sum of squares, SSE. It is the amount of variation in the response not explained by the model. because we don't have a perfect fit, and there is a residual caused by the difference between the observed response yi and the fitted response y hat. And this is a sum of squared residuals. And there's a relationship between these two sum of squares. The total sum of squares, SST, is equal to the sum of the other two, SSR plus SSE. And remember the definition of R squared. R squared is the proportion of variation explained by the model in the total response, in the total variation in the response. Okay, so that means we use SSR over SST to calculate the R squared. This is the proportion of variation in the response explained by the model. And we can also calculate the mean squared error. MSE is equal to SSE over N minus P. And the expected value of MSE is equal to sigma squared. So it is an unbiased estimator of the sigma squared in the linear model. And for the simple linear regression, MSE is just SLF squared. And for the multiple regression, MSE is just SSF squared. So that's why we use these two as estimator of the sigma squared in the model. And we also have the MSR. MSR is the regression mean square. It is SSR divided by P minus 1. So P minus 1 is the number of predictors. Okay, so this is our multiple regression model. Y is equal to beta naught intercept plus beta 1 x1 plus beta 2 x2 to beta p minus 1 x p minus 1. So p parameters. And there were p minus 1 predictors. All right, because we have one parameter for the intercept. And the intercept only reduced model in this. We only have one parameter, which is the intercept. And now we want to do a hypothesis test to decide if the full model works better than the reduced model. So how to understand this sentence? So what we will do to compare this model is just to compare the goodness of fit of these two models. We want to compare these two models by answering this question: is the full model, does the full model explain significantly more variation in the response than the reduced model? Okay. And this is just for the sum of squares. And writing this testing, if the full model works better than the reduced model in a mathematical way. is like this. H naught is just two models. There's no difference in two models. So, or the full model is not better than the reduced model. That means the reduced model is true. Okay, so we use this. So this is our null hypothesis, because in the because the reduced model is nothing but setting those coefficients in the full model to be 0, right? And the alternative is that not all the beta i's are 0. And for some alpha significance level, this is the test statistic we'll be using. So if you remember what we did for the simple linear regression, when the p is 1 or p is 2, right? We only have one predictor. So when p equals 2, h naught is just beta 1 equals 0, and ha is just beta 1 not equal to 0. And we also used this f test statistic. And for SLR, the f we use is SSR over 1, because p is 2 for SLR, and SSE is and we have FSE over n minus 2. So this is actually so SLR is actually the special case for the multiple regression. And the F statistic for the multiple regression is this: SSR over P minus 1 over SSE over n minus P. And this is just MSR divided by MSE. And if H naught is true, and the full model is valid with this error terms, BID, normal 0 sigma squared, then the test statistic F would have a F distribution with P minus 1 and N minus P degrees of freedom. And to reject H naught, we will do this. If the observed F statistic is greater than 1 minus alpha quantile of the F distribution with P minus 1 and N minus P degrees of freedom, then we reject the null hypothesis. And the p-value is just the F statistic, the probability of this F statistic greater than the observed F statistic. And we reject H naught when p-value is small. Okay, so the rejection region is the right tail of of this distribution. Okay, this is a stack loss example. We have three predictors. X1 is the airflow, X2 is the inlet temperature of the cooling water, and X3 is transformed percentage circulating acid. And here's the data. We have 17 observations. So we want to test the full model against the reduced model. So for the full model, we have three predictors. So the full model is this. We have beta naught, beta 1, beta 2, beta 3, 4 parameters. And the reduced model is the intercept only model, only one parameter. And the significance level alpha we used here is 0.05. And the test is whether these three parameters are all equal to 0. Okay. When they are all equal to 0, then that means we use the reduced model. And the test statistic is this. And the assumptions are that the H0 is true and the multiple regression model is true. Okay. And we will reject H0 if F is greater than FB minus 1 and minus P1 minus alpha. So in this case, P is 4 minus 1, and N is 17 and P is 4, so 17 minus 2, and alpha is 0.05, so we use 0.95 quantile. And the value can be found in table P6. So the value is 3.41. And this F statistic, the observed F statistic, can be found in the jump output. If you look at the ANOVA table in the jump output, the F statistic is this F ratio here. And this prob greater than F is the p-value for this test. The degree freedom 3 here is the number of predictors, which is p minus 1. And the degree of freedom for error is just m minus p. Okay. And the squares, sum of squares here, this is just SSR. And this is SSE. And in the mean square column, we have MSR and MSE. And the F ratio is just MSR divided by MSE. And since the F statistic is 169.04, this is greater than the critical value of 3.41. So we will reject H0 and conclude the alternative. So there is overwhelming evidence that at least one of the predictors. So these are three predictors: airflow, inlet temperature, and the percentage circulating acid is important in explaining the variation in the stack loss, right? Because at least one of the slope for one of the beta for these predictors is non-zero. So the response would change when the predictor changes. And one thing to note is that this SSR and SSE are for the formal. Okay. So this SSR is actually SSR 4 and SSE is SSE 4. And this is a more general way to compare different nesting models. And we will see why we use the full model SSR and SSE in the previous test. So if we, what we will do to compare different nesting models is like this. So to compare different nesting models is that we do this test, right? Because when you have nesting models, that means the predictors, some of the predictors used in the full model are not used in the nesting model, right? So if you don't if these predictors XL1, XL2, and XLK are not used in the reduced model, that means beta L1, beta L2, beta LK is equal to 0 for the full model, right? And when these parameters are equal to 0 in the full model, then the full model is just nothing but the reduced model. So the null hypothesis is that the full model is not better than the reduced model. Then mathematically it is beta L1 is equal to beta L2 equals to beta LK equals 0. That's why the null hypothesis is like this, because these predictors XL1 to XLK are not used in the reduced model. And the alternative is that not all of them are 0. So that means the reduced model, the full model is better than the reduced model, right? Because the reduced model is actually not right. We need more parameters. And for example, when you have this hypothesis, beta 2 is equal to beta 3 is equal to 0, and the alternative, either beta 2 or beta 3 is not equal to 0 or both. And the full model is this. You have 4 predictors in beta, not beta 1, beta 2, beta 3, beta 4 are the 5 parameters. So in this case, you're actually testing against a reduced model. Beta 4 xi4. This is a reduced model you're testing. against, right? When beta 2 and beta 3 are equal to 0, that means these two predictors are not used. And the reduced model is just beta naught plus beta 1 xi 1 plus beta 4 xi 4. And the k is just the difference in the number of parameters. In the reduced and the full models. Okay. And you set some significance level alpha. The test statistic is this. The regression sum of squares in the full model minus the regression sum of squares in the reduced model. This much is the extra variation explained by the full model over the reduced model. Right? And k is extra number of parameters. So now you know why we construct such kind of test statistic. It is all about testing the improvement in the variation explained by the model. So if the f value is high, that means a lot more variation can be explained by the full model, and that means the full model is a lot better than the reduced model. And then in this case, we will reject the null hypothesis and conclude the alternative, right? Because the alternative is in favor of full model. And when you look back to this statistic, why we don't have the SSR here? So actually we have the SSR here, because in this case, this p minus 1. So because in this case, the full model is and the reduced is just a beta naught. So k is the difference in the number of parameters. We have p parameters. And in this one we have 1 parameter. That's why k is p minus 1 here. And SSRF is just this SSR here. And what is SSRR? So SSR for the reduced mode. Because we only have one intercept, so the yi hat for this one, the yi hat are all the same, equal to the estimated intercept, and the estimated intercept is just y bar. So the SSR is this, and since y hat is just y bar, so that is y bar minus y bar squared is 0. And then we have SSRF minus SSRR divided by K is just SSR divided by P minus 1. Okay. So this is just a special case for this formula. Okay, and we will, so under the assumption that H0 is true and the full model is right, so that means the multiple regression model is correct. Then the test statistic F would have a distribution of Fk and minus P. And we can construct an ANOVA table like this. We have SSR F and SSR R for the full model and the reduced model. And the number of predictors for these two models are P minus 1 and P minus K minus 1 respectively. And there's K extra parameters in the full model. And the source means that the source of variation. So the source of variation for the S sum of squared here is the full model. And so the SSR is sourced from the reduced model. And the extra variation explained by the full model is sourced from the full model given the reduced model. So this is the extra variation. And we are not interested in the mean squared of the full model and reduced model. We are interested in this extra variation, the mean square of the extra variation. So we have the extra variation divided by the number of extra parameters. And we also have the SSE, and the SSE is based on the full model. And the degrees freedom is n minus p, because we have p parameters in the full model. And the mean squared error is just SSEF divided by n minus p. And the F statistic is MSR of F given R divided by MSCF. So as we have explained before, we will reject H0 and in favor of H alternative when F statistic is large. So in that case, we are in favor of the full model. And the critical value we chose is it should be K. Fk and minus P1 minus alpha. And the p-value is this test statistic is greater than observed F statistic. Okay, so for the stack loss example, remember that the full model is we have three predictors. And the null hypothesis says that beta 2 and beta 3 are 0. So that means yi is equal to beta naught plus beta 1 xi1. So only one predictor in the reduced model. And the test statistic is SSF minus SSR and over k. K is 2 because we have two extra parameters in the full model. And minus p is again 17 observations, and p is the number of parameters in the full model, which is 4. And the reference distribution is fk and minus p. So in this case, k is 2 and minus p is 13. And we will reject the null hypothesis if f is greater than f to 13.95. That's the significance level of alpha is equal to 0.05. The number is 3.81. And we will look at the ANOVA table and jump output for both full model and the reduced model. And you can find the SSR for the full model and the SSR for the reduced model. You find these two numbers and you can construct the ANOVA table for this test. So the extra variation explained by the full model is 20.35, and the mean squared the mean square for the extra variation is 10.18, and the MSE is 1.57. So the F statistic is the ratio of these two, which is 6.48. And since the 6.48, the observed F is greater than that critical value, we will reject H0 and conclude the alternative. Okay, that means, again, we are rejecting that we are in favor of the full model in this case. So that means that there is enough evidence to conclude that at least one of the inlet temperature and the percentage security acid is associated with the stack loss. Okay, because at least the beta 2 and the beta 3, one of the beta 2 and the beta 3 is non-zero. That means when these two, at least one of the change in these two, at least if one of the inlet temperature and the percentage circulating changes, the response would change because the slope, at least one of the slope for these two are not zero. Okay, and if one attempt to eliminate the inlet temperature from water, so what is the inlet temperature? The inlet temperature is x2. So that means the reduced model would be yi is equal to beta naught plus beta 1 xi1 plus beta 3 xi3 plus epsilon I. This is the reduced model. And in the reduced model, we don't use the inlet temperature. And here are the output for the full model and the reduced model. And of course, the test is whether beta 2 is equal to 0 or not, because beta 2 is the slope for the inlet temperature in the full model. And the test statistic is, again, This is f minus SSR divided by k. K is 1 here. And we have the MSE in the denominator. Then, assuming that the null hypothesis is true and the full model is valid with the epsilon IIID, so that means the multiple regression model is a correct full model. And in that case, the reference distribution is F130. Okay. And we will reject F if the observed F is greater than the 0.95 quantile, 4.67. And this is an ANOVA table we constructed from the full and reduced model. The extra variation explained is 18.99, and the mean square is also 18.99 because the extra parameter is just 1. And the MSE is still 1.57. Then the observed F statistic is 12.1, which is greater than 4.67. And we will reject the null hypothesis. So there is enough evidence to conclude that the stack loss varies with inlet temperature. Right? Because the slope is non-zero for the inlet temperature. And the F test for eliminating one parameter is analogous to the T test from what we have seen before. If you check the T test for beta 2, we got a T ratio 3.48 and p-value is 0.0041. And you will see that in this test, we also reject the null hypothesis and conclude the alternative. And if you look at the t value further, if you square it, you get 12.1. What is this? This is just the f we have in this ANOVA F test. So actually, the F test and the T test are equivalent for testing just one single parameter. This is HA here. If you do a two-sided test for one parameter, okay? And this is one thing that is very interesting. And this explains why these two numbers are the same. The F1 nu is always equal to T nu squared. So these two random variables are always equal. And one thing you also need to note that the F test ANOVA if we have one parameter, it's always a two-sided test. Okay. If you only have one parameter, the alternative is always be like beta 2 is not equal to 0. And let's look at the relationship between f and the r squared. So it turns out that the f test statistic can be re-expressed in terms of the coefficient of determination of the form model. If you test this, so you're testing the full model against an intercept only model. And for the stack loss example, the full models R squared is 0.975. So the F statistic, the observed version, is 169 if you use the R squared to calculate it. Okay, so this is the jump output. You have 0.975, and the F is 169, which agrees with the one calculated from R squared. So here is a derivation of the relationship. Remember that the F for this test is SSR divided by P minus 1 and SSE divided by N minus P. And we divide both the numerator and denominator with SST. Then SSR divided by SST is just R squared, and SSE divided by SST is just 1 minus R squared. Okay, then you get this formula. And the same for the test for the full model and a nested reduced model. We have the test statistic can be calculated using the R squared of the full model and the reduced model. So it's R squared of the full model minus R squared of the reduced model over K divided by 1 minus R squared of the full model over N minus P. And for the stack loss example, for the full model, we have the R squared equals to 0.975, and the reduced model has an R squared of 0.95. And the F statistic calculated using the R squared is 6.5. And this is close to the value we have calculated before. We obtained the F of 6.48 from the jump output. And when we tested this one, when we test the beta 2 is equal to 0 or not, the reduced model has an R squared of 0.9517. And the tested statistic we get is 12.117 from just the R squared. And it is also close to the tested statistic we obtained before in the jump output. So the derivation is like this. Again, we are dividing both the denominator and the numerator with SST. Then, because the SST are the same for the full model and the reduced model, and we have this SSF, SSRF over SST minus SSRR over SST. So this is just R squared F, and this is R squared R. And in the denominator, we have SSEF over SST. This is nothing but SST minus SSRF over SST, so that is 1 minus SSRF over SST, which is 1 minus RF squared. So that's why you get this formula. Okay, and that's all for the multiple regression. And next time we will have our last lecture. So that is a extension of the two-sample test, which is the one-way model.